So in the previous example, we looked at calculating average velocities. And I ended the lecture, or that just little example, with the question, and we'll go back to it real fast. We can go back to it right here. You scroll all the way down, which is, what is the speed of the rock at t equals 1? Okay? So in order for us to do that, we're going to start looking at what we call a limit. So if you were to see me out in public in a very informal setting, and you ask me the question, what is a limit? I'm not going to break out a whiteboard and go over everything real fast with you. What I'm going to do is I'm going to give you just kind of like a very simple explanation. So a limit is nothing more than a value that the output of a function approaches when the inputs or when the input values get closer and closer to some value. All right. So here's the example that we looked at in the previous video is the average velocity of a rock being projected upward in the air. And I think, if I remember correctly, the function is s of t equals negative 16t squared plus 96t. And all I have right here is just a very crude drawing of what's happening. But the idea behind this limit is this. If my initial time is 1 and my final time is 2, or I'm sorry, if my final time is 3, what happens if I make my final times within my interval closer and closer and closer to 1? In other words, what if I approach 1 from that way, which is okay. That's called approaching from the right. All right, you're going to hear a lot about that in the next section. So as I approach 1 from the right, what do these output values, and I'm going to just put little dots here on this arrow, what do those values actually start to look like? And more importantly, what is the slope of that line that we're creating? So I have a little demo here in Desmos that I can do. So remember, hopefully you remember, from the average velocity formula, we know that t cannot equal itself. In other words, x1 and x2 cannot equal each other, because if they do, then we have something that is undefined. Also note that my slope here, I calculated, or how I'm calculating it, is the difference quotient. So if you think about that, remember the difference quotient, and I can go back to the previous, let me go back over here. So let's review the difference quotient real quick. So that's going to be in chapter 1. And let me see. Right here. So our difference quotient is nothing more than the slope of the secant line. And a secant line is a line that touches our function twice. So that's shown here in red. And we know that, slope is change in y divided by change in x. So this is, and I'm going to be very crude here the way I'm writing this here. This is going to be y2 minus y1 over x2 minus x1. And if you do all the simplifications here, you get the difference quotient. So I did the same exact thing over here. So let me go back to this example real fast, and boom. I did the same thing here, okay? Now, this h stands for my step size. This h is going to be how far to the right I'm going to allow that second point to be. So what I want you to do is when I hit play, I want you to watch two things. Number one, I want you to watch the point move along the function, and you're going to see the secant line start to form, okay? And then the second thing I want you to look at is going to be the slope, which right now it says undefined, which it should, because, according to the difference quotient, I cannot have a 0 in my denominator. So let me go ahead and hit play, and you're going to see what happens here. So notice that, and let me zoom out a little bit so you can actually see the secant line. There we go. So notice that the secant line is forming, and now it's getting closer and closer and closer and closer to 1 until it gets so close that I stop it at my step size is 0.04, which means my first point is 1,80. My second point is 1.04, 82.534, but most importantly, my slope is 63.36. Now, if I made my step size even closer to 1, let's say 0, 0, oh, too many zeros. How about that right there? Look how close those 2 points are. I mean, if I zoomed in, it's not even going to help us because it starts to look like we just have a straight line. We know that's a curve. And most importantly here, the slope of my average velocity right now is 63.9984. If I were to round that to a whole number, I would just say that's 64. What we're doing is, and this is very, very, very important. Okay, so let me zoom back out here real quick. I just want to show this one more time. All right. And I need to make this 0.1 or else we're going to be here all day watching this just slide. So hit play. Let me zoom out. Come on, I zoomed in way too much. Sorry about that. There we go. So we're going to let this go back and forth. So notice, once again, the slope is getting closer and closer to 64. The further away I get, the further away it is from 64. And like I said, the critical concept here is this. Right now, I'm having secant lines, secant lines, secant lines, secant lines, secant lines, secant lines. If I were to stop this and make this step size 0, a line that touches our function once is called a tangent line. So that's really what I'm trying to do, and that's what a limit is. So let me go ahead and let me write that. Let me write that underneath here. So as t1, which is going to be some arbitrary value, it's going to be some step size further away from t. So as t1 starts to approach, as t1 approaches t sub 0, the average velocities approach a unique number. Okay, so they start to approach a unique number. This unique number, and now I can finally zoom out so I can show you what it is. The unique number is called the instantaneous velocity. Okay, and that's where we have a line that only touches our function once. So up top here on that graph, let me try to do this as neat as possible here. I'm going to erase all this stuff here. We're going to have this going like this. I'm no longer concerned with S3 or T3. This is the point right here. And in red, I'm going to draw what we call a tangent line. We're going to be finding a lot of equations of tangent lines in the next coming sections. Okay? So remember, as T1 approaches your initial T value, all those average velocities start to approach a unique number. That unique number is called the instantaneous velocity. Mathematically, that looks like this on the left-hand side. The limit as t approaches 1 of the average velocities is going to equal, and that's what I have down here. So let me underline what I'm talking about. So that's limit notation, and we read that as the limit as t approaches 1. So we're going to allow our values to get closer and closer and closer to the value 1, but it'll never actually be 1, because if it's 1, we get 0 in a denominator. So we let this get infinitely close to 1. The arrows are going to be the arbitrary point. That's going to be that point 2 that we're going to let get closer and closer and closer to our first point. In this case, it's going to be t equals 1. And if we allow that to happen, as you saw in the graph, we start to approach that value, 64 feet. Okay? So I hope that helps to explain instantaneous velocity and what a tangent line is. In the next section, we are going to go over definitions of limits. So we're going to be looking at one-sided limits, two-sided limits and what they mean. And then we're going to look at certain graphs and determine what the limit is just by inspecting a graph. In section 3, that is where we learn techniques for computing limits. Like, how do you actually compute this? using calculus and using algebra other than just looking at a graph. So I will see you in the next video.